So I'm recording. So I am going to discuss lesson 1.6 today as per our plan. So we're going to discuss calculations of limits using some algebraic rules. That's what we learned today. Then we're going to discuss about continuity and the precise definition of limit continuity, and we'll finish up the chapter. Um, all right, so I'm going to share with you the whiteboard. Let's screen sharing. I'm not seeing the whiteboard here, so let's do again. Okay, there we go. That. Okay, so now there we go. So now it's working. I think you can see here. And our lesson today is, as I said, 1.6, calculating limits using limit laws. Calculating limits using limit laws. All right, so what are these limit laws that we're talking about? Well, very simple limits. So I'm not going to teach the concept the way it is in the book. I like to teach the concept based on some examples. And then at the end of the hour, we'll figure out what those limit laws are and what they were really about. So I'm gonna use some sort of shortcut, but I think it's more intuitive and it's better to teach it this way. And I've been doing this for some time, so this is kind of I think the good approach. All right, so here's a limit. Limit something like this. Limit as x goes to, and I'm gonna copy a problem from here from the book. I don't know. Limit as x goes to just make up some problem. Limit as x goes to 3 of 2x squared minus 1. Let's say that. So intuitively, what's going to happen here, I think that everybody will agree with me that if we approach 3, so the idea is to approach 3 from the left and from the right? But so generally, if we approach 3 with x, right? So if we give values of x that are very, very close to 3. What do you think is going to happen with the values of 2x squared minus 1? Well, what's going to happen with these values here, as x goes closer and closer to 3, x squared goes closer and closer to 9, right? Because it's, I don't think there's any surprise there. 2x squared goes closer and closer to 2 times 9 or 18, and then subtract 1. So the limit you would guess would be 17. And how did we find this limit again? Simply by substitution. So if you substitute x equals 3 in the formula here, you will get that. You will get 17. And this is the nicest way to calculate limits algebraically. You don't have to do a table. If you can somehow substitute in your formula, do substitute, and you get the limit. So I will say this is not a law, it's a procedure if you want. I will say that the first procedure that we learned today is to try substitution. And this is really the first thing that you want to try when you calculate the limit. Try to substitute and see if it works in the formula. So for example, the limit as x approaches 1. Oops. 1 second. Just clean this up here. Limit as x approaches 1 of x minus 1 divided by x plus 2. What would that be if I substitute 1 in this formula? And I can, because everything makes sense. 0 at the top, 3 at the bottom. So I would get 0 divided by 3, and 0 divided into 3 parts. 0 divided in 3 parts is also 0. So substitution very much works in this case. So we basically made x equals 1 in the formula. All right, so that would be our first strategy to calculate limits. Now, our second strategy, if substitution doesn't work, what happens if substitution doesn't work? Well, if substitution doesn't work, you would want to try something like maybe simplification. Here's the situation. Limit as x goes to 1, x squared minus 1 divided by x minus 1. We did this kind of thing earlier in the semester when we calculated, the slope of a tangent line. And if you remember, and I want everybody to remember, folks, the algebra that's behind this formula here, this is gonna be x squared minus 1 can be factored nicely. And does anybody remember what x squared minus 1 how x squared minus 1 can be factored? You can say in the chat, folks. This is something important that you might want to brush up if you've forgotten that. So how does x squared minus 1 factor? Let's see. Anybody in the chat can? Yeah. Let's see. So there we go. So there's Sam and Sammy. So I don't remember. Sammy, is it a he or a she? Have several Sams. Okay, she. Okay, so Sammy says that it's x minus 1, x plus 1. That's very good. Excellent. Thank you. So this is okay. So it's x minus 1, x plus 1. Let's do what Sammy said. And then we do x minus 1 here, and we can see that these things can be simplified. So this is what I like most, when I have common factors, top and bottom, I just get rid of them so that we can say here, oh, this is just the limit as x approaches 1 of, instead of saying x squared minus 1 over x minus 1, I would just say x plus 1. And, this is now suitable for substitution. So we can say 1 plus 1 in the formula, and that is equal to 2. So that is the substitution that we can perform here. All right, so the second method that I emphasize here, the second approach to limits, so besides substitution, if substitution doesn't work, by the way, I forgot to say that, but why doesn't substitution work here, folks? Why do you think that I even didn't bother to say anything about substitution? Because I saw from the get-go it doesn't work. Can you say briefly in the chat why substitution would not work here, folks? Why is it that it doesn't work, direct substitution? In the formula here, the one I start with here, in this formula, why is substitution not working in this guy here? All right, so let's see, anybody in the chat? Or you can open up your mic, folks, and say that loudly here. Let's see, anybody who wants to tell me why substitution would not work here? All right, that's a bunch of answers here. Yes, Nathan says, because if you substitute 1 in the denominator, you will get 0, and you can divide by 0. That is correct. And Sammy also said the denominator would be 0. That's correct, folks. You got it. So we can't substitute. So you can't substitute x equals 1 because denominator becomes 0, and you don't want to have that sort of thing. So you don't want to have denominator 0. That's a mistake, a huge mistake in math. So substitution doesn't work. Then we try to simplify and then substitute if we can after that. All right, so that will be the second procedure here that we learn. This is called simplification. All right, there's one more strategy that we can employ when we calculate limits. Again, we calculate these limits algebraically, folks. So in contrast to what we did up to this point where we did tables and things like that, This algebraic approach is more elegant. You know, you can sometimes say very quickly what the limit is without having to go through the pain of, you know, of, sorry about that, without having to go through the pain of, doing the tables and going to the online calculator and things like that, which is, you know, not a difficult thing, but, it takes a bit of time. So the next thing that I'm going to do here is give another example. And this is an example that's a bit high powered. You know, it's a little more complex than the usual ones. So let's say we want to calculate this limit. Limit as x goes to 1 of, over here, I would have square root of x minus 3. I'm going to say, instead of, you know what, I'm going to change the limit here. So I'm going to say, instead of x goes to 1, I'm going to say, apologies, folks, x goes to 9. So square root of x minus 3, and over here, x minus 9 at the top. So what happens if I try to calculate this particular limit? Would substitution work? No, for the same reason that simplification, in the previous example, substitution didn't work. If you substitute 9 in here, you get 0 at the top, 0 at the bottom, because square root of 9 is 3. And then you get 0 over 0. That's not correct. So it would not be correct to have denominators of 0. All right, now speaking of square roots, folks, I saw some uneasiness about working with square roots on the quiz. This is one of the things that I want you to review, because we're going to use square roots quite intensively here. Many examples will have square roots or some other types of roots. So do remember that square roots can never be a negative number. So I want everybody to remember that, because I noticed a selection of graphs. You know, you had square root of something, and a bunch of people selected to do some graph that was not above the x-axis. So there was either a line going down or some other sort of shape that was below the x-axis. So that will never happen. So square roots, remember, they're always positive numbers. When you take the square root of 9, you always get 3. Of course, the equation x squared equals 9 would have a second solution, negative 3, but that's not the square root. All right. So that being said, let's work on this problem. This problem has a trick. So the trick is, folks, to use conjugates. Now, I don't recall if you, we didn't review conjugates here, and I don't recall, I don't remember, I don't know actually what exactly you learned in college algebra classes. So for instance, in high schools or whenever you took college algebra, if you took it here, if you actually did conjugates when you covered the square roots. So it's not a complicated topic. I can review it with you here very quickly, but we're not going to go into the depth that a college algebra class would go. In other words, I'm just going to tell you how the thing works, but I'm not going to do a lot of explaining of the formula. I'm going to do enough explaining, but again, not to the point where we would do a comprehensive review of the topic of square roots or radicals. So what happens here, folks, when I see x minus 9 over square root of x minus 3, can copy that thing. I'm going to say, you know what, this is going to be the same as, and I'm going to multiply by conjugates. What conjugates are there here? In this case, the conjugate, I'm looking at the quantity that has a square root, this one here, and it's a square root minus something. And I'm going to say, you know what, let's multiply by square root of x plus that thing, plus 3. So let's change the sign between the square root and 3 and multiply by that thing. And now, since you wanna keep the formula that you had earlier here, So sorry about that, it's kind of moving around here. You want to keep this formula. What you want to do, you want to make sure that when you, if you divide by square root of x plus 3, you also multiply by that thing, by square root of x plus 3. So this guy here that I'm multiplying by, this is simply 1. So in essence, I'm not doing anything of any sort of meaning to the formula. I'm not changing it. I'm just leaving the exact same thing. It's still x minus 9 over square root of x minus 3. The reason why I'm multiplying by this guy, again, this is called the conjugate, is because that's going to simplify the formula that had a square root. Now, it might look puzzling. How is it that we're going to simplify the formula when we're going to multiply by this kind of thing here? Well, you will see how the formula will indeed simplify. All right, so here's what we do, folks. The trick is, so once you multiply by this conjugate, the trick is to multiply both top and bottom by, multiply the two fractions here. So when you multiply two fractions, you multiply the numerators, you multiply the denominators. So I'm going to say here at the top, x minus 9 times square root of x plus 3. And at the bottom, I'm going to say square root of x minus 3 times square root of x plus 3. And now if you look in the chat where Nathan and Sammy answered and stuff, you will see that we actually ran into this situation when we multiply the difference times the sum of two numbers. And it was there for x minus 1 times x plus 1. If you recall, so I didn't, it was intentional that I chose the previous example, this one here. Oops, it's covering my screen. Sorry about that, folks. I have a small screen here, gets covered by other things. So if you look at this example here, this is kind of the same in a way with the one that we're studying right now in example 3, because over here we had x minus 1 times x plus 1, and we saw that the result of that was x squared minus 1. Well, guess what? The exact same situation over here. So when we multiply the difference over here at the bottom, the difference times the sum of two numbers, what happens, and this is what I'm going to focus on right now on the bottom part of a fraction, this is going to be the first one squared minus the second one squared. So that's kind of what the formula does. And this is the reason why I'm doing this conjugate, because when I multiply a minus b times a plus b, or x plus 1, x minus 1, or stuff like that, I always get square minus square. So I get the square of the first entry and minus the square of the second entry, which in this case, because it's square root squared, that's going to end up being just x. And over here, minus 3 squared, which is going to be minus 9. That's going to be our formula. Is that good, folks? So it's very important to remember that this product here will end up being x minus 9. So we'll end up being without a square root. And that is the reason why I did the multiplication by the conjugate. At the top, we leave the way it is because we're going to be able to simplify. And the promised simplification, I think, it's fairly obvious. So look here, x minus 9 and x minus 9, they go away. And we really end up with a very, very simple thing. That's very square root of x plus 3. Kind of like the problem that I put on the quiz, but I failed to put the, so I didn't pay attention. I failed to put the correct answer for that. So this is what the answer would be for this particular problem, square root of x plus 3. Now, let's remember, let's not lose track of what we were doing here. We worked out the algebra, so the simplification, we multiply by the conjugate, we did some simplification, some cancellations here, and we got that, but we still have to calculate the limit as x approaches 9, because we didn't do that. That should be a number, right? The limit is always a number, so or infinity plus minus infinity. So we need to still need to calculate this thing. So we did simplify this fraction, which is horrible. You know, if you start to look at it, it's x minus 9 square root of x minus 3. We made it even more complex before we were able to simplify, but it did simplify, and that's going to be the case all the time. It does simplify to a form where I can say, you know what, this is really easy right now because I can simply substitute. And if I substitute, this is going to be the square root of 9 plus 3, and that's going to end up being, so it's 6, right? 3 plus 3. All right, so this method here, that method is called the use of conjugates. And it's only suitable when you have square roots or some other types of roots. If you don't have square roots, forget about this, you know, with square roots. It's probably not going to help if you don't have square roots. So these are the three, I'm going to put here number 3 example. These are the 3 examples of 3 key topics of today's lesson. And what's going to happen next? So I'm going to put these in some context. So you should be able, following these 3 examples, to do many of the problems in the book, and I'm going to point some examples over here. So for example, let's do number 11 from the book. And so far so good, folks. Let me know if there are any questions because I'm moving on to doing some other problems. So these are these examples. Again, if you look in the book, these are just what I just told you here. They don't formalize them clearly, and I always found that confusing. But why they don't choose to formalize them nicely? But instead, they just say applications or something. It's applications, but it's gotta be taken care of properly. Otherwise, it's confusing. So what I'm gonna do, folks, see there are no questions here. I'm going to discuss some problems. So now these are further examples, and these examples will highlight one or other of the techniques that we just learned. Number 11 from section 1.6. We calculate the limit as x goes to 5 of x squared minus 6x plus 5 divided by x minus 5. All right. So, so this is, how do we do this problem, folks? Now, if we substitute, of course, we can do any of these problems, by the way, it can be done by simply, you know, using tables. So you can do that if you want. In fact, let's do this with a table and let's see what happens. And then we'll do it algebraically. So I'm going to stop sharing this screen with you, folks. And I'm going to move on to a table and to do, okay, so I'm going to do this thing here. So let's do Desmos. All right, and Desmos is on the screen, graphing calculator. And again, so we calculate the limits. I'm just going to write the function here. So I'm going to say the function is f of x equal to, and looking at the formula, x squared minus, so it's going to be, I'm going to use a pair of parentheses, so x squared minus 6x plus 5 divided by, and the bottom will be x minus 5. All right, so this is what I want to use, and I want to calculate. I'm going to write a note to myself here. I want to calculate limit as x approaches 5 of this function f of x. All right, and over here I'm going to do the table like we did before. So we're going to do a table, I'm going to wipe out these letters. I'm going to say t and f of t in the table. Oops, f of t. There we go. And we're going to give values to x very close to 5. So for example, let's say 5.1. All right, then we're going to do 5.01. And we're going to do 5 point, even closer to 1, 5.001, a bunch of zeros. And as you can see, I think it's pretty clear from the way things go here. So as I go very close to 5 with t, f of t gets very close to 4, which is about the correct trend. So I'm pretty sure that if I use values of x that are less than 5, let's say 4.9, let's see what happens there. Yeah, 3.9. If we do 4 point in the same table, I'm doing it here. 3.99, yeah, there's a 4.999. There we go, 3.999. So very, very obvious. Yeah, this is going to trend to 4. So let's see with algebra. Let's do this thing with algebra. Let's stop this share. All right, and let's change to our. Second, I was clicking on the wrong thing. Our whiteboard, and let's do this with algebra. And this is the calculation that I'm going to perform right now. And I'm going to say, you know what? I cannot substitute 5 in here. So that will be my first attempt to substitute 5. I cannot substitute 5 because if I do, I get something over 0. And I don't want to have 0 in the denominator. So my chance would be to approach. So we learned 2 other things. One of them was to simplify. And the other one was to use conjugates. But we said that conjugates only when you have square roots. You don't have any square roots here, so forget about conjugates. So what we're going to have to do, we're going to have to attempt to simplify this. Now let's look at the fraction here. So what is a fraction? X squared minus 6x plus 5 divided by x minus 5. What can we do to simplify this? At the bottom, you can't do anything. It's simple enough. It can't be simplified anymore. However, the top can be simplified, can be factored. So this is where you need to review a little bit of factoring of trinomials from college algebra again. And if anybody remembers how to factor this trinomial, please say in the chat. This one at the top here, I'm focusing on the top part. So how do you factor x squared minus 6x plus 5? Can anybody remember that, folks? Okay, so there we go. There's Caleb, and he says x minus 5, x minus 1, and that is correct. So now, let's see, how did Caleb figure out that there's negative 1 and 5? Let me write down x minus 5, x minus 1. You said, right? All right. How did we figure out that it's x minus 5, x minus 1, and not some other numbers? So you look for these numbers, folks, for 5 and 1, these solutions. It's always going to be x minus 1, x minus something, x minus something else. You look at these numbers as the factors of 5. And so you can easily figure out that the factors of 5 are 5 and 1, or negative 5 and negative 1, things like that. And then the second thing is you want the ones that you subtract here to add up to negative 6, and they add up to negative 6. So their product has got to be 5, and their sum has got to be this one, negative 6. So yeah, that's x minus 5, x minus 1. That's the only options. And then you put x minus 5 at the bottom, and look at what happens, folks. So you see here, x minus 5 cancels out, and we end up with x minus 1. Now, let's not forget, this is not the answer. So remember, you want to end up with a number for the answer. So this is still an incomplete answer, and you would get penalized if you write that on the test. So what you want to say, oh, but I want to calculate the limit as x goes to 5 of x minus 1. And that is 5 minus 1, folks. We can do a substitution at this point in time, and 5 minus 1 ends up being indeed 4, which is what we guessed with the tables. With a table, so that's the limit for x minus 1. And this is excellent because this is a good example of where you involve a more, I would say, sophisticated type of simplification, not just a straightforward one. And some of the other examples in the book have even more simplification than this. So, for example, if you look at problem 14 or problem 15 or so, or even problem 12, they all have some other type of simplification that's way more sophisticated than this one that we did here. And then number 17 would be the utmost, the biggest challenge in terms of simplification. So try number 17 at home. I'm not going to do that here today. Try that at home and see how that works. You will see that you have to put a little bit of effort to get that solved. All right, so as I said, I'm not going to do that. Do it at home, and then let me know how that works next time around. What I'm going to do here, I'm going to do another problem that, so I'm going to close the lesson with this one here. This is going to be our last problem here. So I'm going to change pages here. I'm going to do the second problem today. The second will be the fifth or so. Number 21. Another problem from the book. It's from your homework, from section 1.6. Limit as h approaches 0 of square root of 9 plus h minus 3 divided by h. All right, and this is going to be equal to the following. Now, again, if you substitute 0, you will not get something very good, because this is going to be a number like square root of 9 minus 3, where there's going to be 0 eventually at the top and 0 at the bottom, which is worse. So this is not possible, and then you have to think, oh, what am I going to do? Am I simplifying, or am I going to use conjugates? In this case, because there's a square root, I think your best option, again, this is not something that you have to do necessarily this way, but your best option really is to use conjugates. And what is the conjugate that I'm going to take? So I'm going to take the expression separately here, square root of 9 plus h minus 3 over h, and I'm going to say times, and I'm going to use conjugates. The conjugate would be the conjugate for the top part here, which is square root of 9 plus h. So again, the quantity under the square root is 9 plus h plus 3. Let me make that square root nice, for whatever reason, kind of ugly square root. All right, there we go. So so that will be the conjugate. So again, if you have a square root quantity minus 3, the conjugate will be square root plus 3. All right, and then divided by the same thing, by the square root of 9 plus h plus 3, because again, you want this to be 1, essentially, this guy here, so that you still keep the initial expression, right? But this is going to be, and the trick that I taught you goes like this. So we're going to multiply, on levels now. So we're going to multiply square root of 9 plus h minus 3 times square root of 9 plus h plus 3 divided by h times square root of 9 plus h. First, we write them nicely like that, so we see what's happening, and then we do other things. And I'm gonna look at the square roots, and I'm gonna see again. I'm gonna recognize that pattern that I just told you about. A number minus another number, the number plus that number. the plus b other number. So, so there's two numbers, a and b, and you have a minus b, and then you have a plus b. How do you multiply these two? Well, you basically do the difference of squares. This is some formula that I want everybody to remember, and let me write it down over here again. A squared minus b squared, remember, is a minus b times a plus b. You want to remember this formula from your college algebra days. And that's what's working here. And that's why I said that I didn't do a full review. This is something that you want to remember. But right now, when you do the product here, you will get a very simple thing. You will get something like, and this is, so let's pay attention here. So we get something, square root of 9 plus h squared will be 9 plus h quantity, let's say, and then minus 3 squared, which is minus 9. And that's going to be divided by h times square root of 9 plus h plus 3. And over here we have, so now let's see how do we do the difference. From 9 plus h, if we subtract 9, the 9s will cancel out. And I'm going to be left with simply h at the top and at the bottom h times square root of 9 plus h plus 3. And look at this here, there is further, so there was cancellation at the top, and there is cancellation across, the fraction line. So so simplify h, and we're gonna have here, folks, 1 over, and at the bottom we're gonna have 9 plus h square root plus 3. And that's gonna be the thing. So it's gonna be 1 over square root of 9 plus h plus 3. All right. Now, this is not done. We have to calculate the limit as h goes to 0, right? So, so this thing here is the one we want to calculate. The limit as h goes to 0, 1 over square root of 9 plus h plus 3, and that's going to be equal to, and then if you look carefully here, what you see, folks, is well, this is going to be 1 over, and we can substitute. That's the trick here. So, so this is simplified enough. This guy is simplified enough here to the point where I can substitute 0 and I can get something that makes sense. So this is going to be square root of 0 plus 9 plus 0, or 9 if you want, plus 3. And that simplifies to be 1 over, this guy is going to be 3 plus 3, 1 over 6. That's going to be the answer to my limit. Now, this limit would be harder to guess with a table because, 1 over 6 is not one of your numbers that's, 0.5 or 0.4 or something like that. It's going to be a number with some sort of periodicity. So it's going to be an infinite number of digits, and it's kind of hard to guess, and especially when there's an infinite number of digits for the number. It's kind of hard to guess what the number really is. So, so this is how you do this problem algebraically. Now, this is probably the most high-powered example that we do here in this section. All right. So that being said, we're almost done for today. What I want to do, I want to go back and I want to point out what those limit laws are, the ones that they present in the book. So by the way, folks, so the way I teach here, I like to teach by sort of going backwards. So the method of direct substitution is emphasized on page 65, but that's towards the end of the lesson. And I like to start with that because that's what people do in practice most of the time. They start with these substitutions and then simplifications and then conjugates. So nobody really memorizes these rules that are at the beginning. But the rules are very simple. So the rules that these people are saying, so what happens when you want to calculate a limit? So, so when you fabricate a function from two other functions, what you can do, you can take the sum of two functions, and you might say, what happens if the limit as x goes to a of f of x is some number, let's say L1, and the limit as x approaches a of g of x, what happens when this is L2? Well, folks, really, the sum, their sum the f plus g, as x approaches a, f of x approaches L1, g of x approaches L2, the sum will approach L1 plus L2. So it's not so hard to guess what happens. And people say in the book, the limit, it's a bit abstract here, the limit of f plus g as x approaches a, f plus g of x is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. And that goes by extension. So this strategy goes by extension. So you can replace the addition sign here by multiplication, and you still get a true rule. So that's going to be the limit of f times the limit of g. All right, here. So so that goes by extension. Or if you replace the plus sign by subtraction, you will get the difference of limits. And when you can divide, it works for the quotient too. So except that the case when the quotient is undefined at the point there. So so I'm not going to be very persistent about these rules. I'm going to give examples next time, not today, how these rules are applied, the abstract rules. But focus on those that we did at the beginning of the hour, the procedures, because those are going to be the procedures that you are going to use in practice for sure. All right, so this is about all I have to say here. I'm going to give some examples, some further examples tomorrow. By the way, what we calculated in one of the previous examples, in this example here, we're going to take another look at this, because this, what we do here is a derivative, really. So we're going to take another look at that in maybe a week or so, and we will see how nice this fits with a general formula for those derivatives. All right. This being said, I'm going to close the lesson here. I'm going to stop the recording. I'm going to stop the share as well. If you have any questions, folks, do let me know.